Thank you very much, and just let me begin by thanking the Taiwanese EPA for inviting me here. It's definitely an honour to be here, and to the organising committee. This is my first time in Taiwan, and it made me feel very welcome, so that's really appreciated. Induced seismicity and carbon capture and storage, something of a sensitive topic I'm well aware of. At lunch, Dr. Adair made a suggestion to me, which is, make sure you set your position statement out early doors. And I think I'll do just that before we get into the meat of my talk. We know injecting fluids into the subsurface can trigger earthquakes. Not often, but it does happen. But when you look at, and as you've seen in some of the talks this morning, the likelihood of us meeting our various climate change objectives without CCS and the potential consequences of failing to meet those targets, I think the risks of not doing CCS are far worse than the risks of doing it. If we meet our objectives, and there are hundreds of carbon capture and storage sites around the world, I'd be willing to bet at least one or two of them may well trigger some felt earthquakes. But when you compare the risk of climate change and increased typhoons, rising sea level, and the like, I think the risk of a few medium-sized earthquakes compared to those risks are actually fairly small. So, moving forward, we've known for a long time that injecting fluids into the subsurface can trigger seismicity. This is the data from the Rocky Mountain Arsenal near Denver in the USA in the 1960s. And the upper plot shows the rate of wastewater injection into the subsurface, and the lower plot shows the rate of earthquakes felt in the nearby town of Derby. And you can see pretty strong correlation between the amount of fluid being injected and the triggering of these seismic events. So that was kind of the first time that we realized as humans that injecting fluids into the ground can trigger earthquakes. And the largest event here was a magnitude 5, so it's kind of I'd say that's pretty a moderately sized earthquake. Definitely large enough to be felt, potentially large enough to do a small amount of damage, but not sort of the really large earthquakes. Most of us are aware of what's happening in the USA at the moment with the shale gas revolution, and that's led to a substantial increase in the amount of waste fluids from the fracking operations that need to be disposed of somehow. Now you can treat this water and recycle it and then put it back into a stream or to the ocean, but a lot of places in the US, what they do is they drill class 2 injection well, as it's known, and inject the waste fluid into deep aquifers. And that's been associated with an increase in the seismicity in the mid-continental USA. So you can see in this plot here, this is kind of the background rate from the 1970s, and you can see in recent years this uptick, this increase in the number of earthquakes that have been felt in the mid-continent. This is a paper by Bill Ellsworth from the US Geological Survey last year. And here are a few sites where injection has been associated with seismicity. Now some of these it's debated, some people say it's natural, it's not due to injection, but these are sites where at least someone in the peer-reviewed literature has said fluid injection has caused an earthquake. So as I mentioned, the Rocky Mountain Arsenal event, magnitude 5.3 back in the 1960s. There are a couple in Ohio in the mid-1980s. Again, magnitude 5 was the larger one in Perry in 1986. And then with the onset of the shale gas revolution and unconventional gas, some of these in Texas, Arkansas, and Oklahoma. The largest event, magnitude 5.7, Prague, Oklahoma, did actually do a fair bit of damage. About 14 houses were knocked down. It's quite a rural area, but there was some damage associated with that. Most of the events kind of slightly smaller, so magnitude 3, magnitude 4. In Europe, so I'm coming from the UK, so I'll talk a bit about the European perspective as well. We don't quite inject the same amount of fluid, so most of the oil production in Europe is in the North Sea, and their wastewater is just dumped into the North Sea. But we also inject natural gas for gas storage, as the previous speaker mentioned. And there was a recent case in the summer last year, a new natural gas storage facility began injecting natural gas off the eastern coast of Spain. And pretty soon afterwards, a fair amount of seismicity was picked up associated with this gas injection well. And now injection there has been paused while investigations are carried out, but obviously the companies involved invested a lot of money in new wells, new drilling rig, and if it turns out that they can't continue injection, then there's a very large amount of investment, over €1 billion invested that could be lost if they can't find a way to inject without triggering earthquakes. And this is just a map of these events. So we're off the eastern coast of Spain. This is where the rig is, and you can see all of that cluster of seismicity associated with the injection. So the largest event was 4.2. There were several events of about magnitude 4. These were felt along the coast, and the local people there got very upset. They weren't large enough to cause significant damage, but the local people were still very upset, and that local upset forced the temporary halt, at least to this project, with questions being asked as to whether it will ever be allowed to continue for now. Just to note, this is the same map just zoomed in. This is historical seismicity in Spain, and there was really no seismicity in this area before this injection began. So there may have been earthquakes here in the past. We only have earthquake records for the last 30, 40 years in most cases, but certainly during that time there was no warning of any natural seismicity here before this injection started. As I said, sometimes it can be difficult to determine whether an event is induced, or is it just naturally occurring and by coincidence it happened to occur near to your operation. So we're still in the community, the kind of seismology community, there's the kind of Davis and Froelich criteria from people back in the early 90s. So some of the questions we ask, it's not you have to be all yes or you have to be all no. It's just a kind of guideline really. But are these kind of the first events of this type, of this character in this region, or have you had similar events in the past, which might tell you whether it's natural or not? Is there a clear temporal correlation between injection and seismicity? So you saw in one of those first slides that correlation between injection rate and the seismicity rate, really giving the indication that was the injection that's triggering seismicity. So that's often a good indicator. Obviously, you want your epicenters near wells, although how near is still a question. How close do you have to be for an event to be to your injection well for you to say we caused that or we didn't cause that. Similarly, in depth, are your earthquakes occurring at the same depth you're injecting at, or are they occurring much deeper? The difference being if it's much deeper, then maybe you're not the cause of it. And then finally, are you injecting enough fluid, changing the pressure by enough to trigger events? If you are changing the pressure, or if you're not changing the pressure, that's an interesting question to ask there. Why does injection trigger seismicity? So this is called a Moore circle plot. So if anyone in this room is geologists, then I'm sure you fully understand it already, but I will explain it in more simple terms because I know, I'm sat next to a lawyer at least, and I'm sure he'd like an explanation, even if no one else would. So if you put your hands together and try and slide them past, it's very easy to slide them past. Now squeeze your hands together hard, it becomes harder to slide it past. So there's two forces acting. There's the force normal, which is how hard things are squishing together, and there's the shear force, which is trying to slide things past. So if I'm holding my hands together, there's two ways I can get my hands to slide, two ways I can get the fault to move. I could try and slide harder. That would be increasing the shear stress, which is the y-axis on this plot. So increasing the shear stress, move ourselves up, cross this line from stability into sliding. The other way of doing that is to push my hands together less. So rather than squeezing things really hard, now squeeze things slightly less, and the same force that couldn't move the fault before now is able to move it. And that is reducing the normal stress. So rather than moving up to cross this line, I move to the left to cross this line. The effect is the same. I move from the stable to the unstable regime, potentially triggering an earthquake. And that's exactly what increasing the pore pressure by injecting fluids into the subsurface does. You don't change the shear stress, you change the normal stress, kind of reducing the friction on that fault and allowing it to slide where it was unable to slide before. Now there's two key factors about this plot beyond the basic demonstration that it's important to kind of take home. One is that you need to have a fault to have an earthquake on. You're not kind of creating a fault from scratch where there was no fault before. You need to have a fault on which to be squeezing or not squeezing. Without that fault, there's no earthquake. And the second is that fault has to be kind of optimally orientated in the present day stress field. So the reason this is a circle rather than a single point is that this circle represents faults arranged at any possible angle. But of course, if my fault is the wrong angle, it's down here at this angle or this angle, I can change the normal stress as much as I want. It's never going to hit that failure envelope. Only faults that are at the optimum orientation, so in this case, this particular orientation, at this point on the Moore circle, will hit this line and fail. So you need to have a fault, and it needs to be correctly orientated in the stress field such that it's capable of failing. So not all faults will trigger earthquakes, which is good news, I guess, if we're planning to do CCS without triggering seismicity. I work in a number of fields, not just carbon capture and storage. Subsurface fluid injection is common for all of them. Natural gas storage, geothermal systems, hydraulic fracturing and shale gas, as we talked about, waste fluid injection from oil fields, and carbon capture and storage. All these things have the potential to induce seismic activity, and we have documented literature of all these systems triggering induced seismicity. So CCS isn't unique in that respect at all. And as the previous speaker said, we can learn from some of these other systems. CCS is something new, but there are similarities with things we've done before, and we should be looking to learn from these things so that we can kind of have a better understanding of what's going to happen in the subsurface. From a UK perspective, as I say, carbon capture and storage is a big part of the UK government's plans to reduce CO2 emissions. These brown dots show large CO2 emitters, and our plan is to put it all in the North Sea where there's old oil fields and saline aquifers. The two main projects, White Rose in East Yorkshire, going to the southern North Sea, and Peterhead in Aberdeenshire, going out to the northern North Sea. And the UK government's invested over £1 billion in a kind of commercialisation demonstration competition. So there's a lot of money there from the government to get CCS off the ground. So why is induced seismicity an issue in CCS beyond the very obvious, we don't want to trigger large earthquakes that damage someone's house? Well, as we saw in Spain, even if the earthquake's not large enough to actually cause damage, public perception is a potentially big issue. So even if you say to the public, oh yeah, there'll be earthquakes, but they're not going to be big enough to cause any damage, I don't think the public really take that argument too kindly. They don't want to see any seismicity at all, regardless of how large it is. But there's another couple of issues that are kind of a little bit more unique to CCS than some of these other issues like oil fields, waste disposal, and that's that CO2 is buoyant and it will want to rise back to the surface. So we have the added issue that if we're inducing seismicity, are we putting the integrity of our cap rock at risk, and also are we putting the integrity of our wellbores at risk? If we've got geomechanical deformation in the subsurface and shearing along beds, for instance, are we at risk of shearing a wellbore, damaging the integrity of the cement, which is a potential leakage pathway that might be expensive to remediate? You certainly can remediate it, but that's an extra cost that you don't want to have to deal with. You want to minimise how much this project is going to cost. So, as I said, we want to learn from previous examples of induced seismicity, particularly these many examples of induced seismicity from oil field waste disposal, so that we're not coming into CCS completely blind. So sort of a number of questions we might want to answer. Are there any controls on the maximum magnitudes? Is there anything I can say about the volume I'm going to inject to start with that will say, I can guarantee I'm not going to cause an earthquake larger than magnitude, whatever, based on what volume we're injecting? That's still very much an open question, so I'm not going to try and answer that one today, although there are a number of papers in the literature that have attempted to answer this with varying degrees of success. But the aerial distribution of events, how far away from my injection well am I able to trigger seismicity? That's a very important question, because we need to know, okay, how far away from my injection site do I need to make sure that I find faults that might be able to trigger? Is a fault 20 kilometers away at risk from my injection project? 30 kilometers away, 40 kilometers away? What's the question? We saw in some of these examples already, there are faults relatively nearby, kilometers away, but is kilometers away sufficiently far away that you can't induce seismicity on these faults? Similarly, the depth distribution of events. Do most of the events occur in the reservoir, above the reservoir, below the reservoir? I'd contend that events a long way below the reservoir are kind of a good news, because events above the reservoir might suggest there's a path for leakage, but events a long way below the reservoir kind of tell us, well, that's probably not going to be a risk in terms of leakage. Of course, we don't want any induced seismicity at all, but an induced event kilometres below the reservoir doesn't concern me as much. And finally, what can we learn about the various monitoring strategies that people have put in place? You know, what are the key things we need to do to properly identify these risks at an early stage, so we can mitigate any problems immediately, rather than waiting for a large event and then go, oh, that was a mistake. But get in there early and monitor effectively. So just in terms of injection rates and volumes, from some of these examples that I'm going to talk about, this left plot shows the injection rate, and the right-hand plot shows the total injection volume when the largest event occurred. And these various abbreviations are these various sites in the US where oilfield waste disposal has triggered seismic activity. And the green columns on the right of both plots are those two UK projects I mentioned, the White Rose and the Peterhead projects. That's the volume, reservoir temperature and pressure that they're proposing to inject at these projects. So you can see the injection volumes on the whole substantially larger than injection rates and volumes that we know have triggered, moderate-sized earthquakes in the US. So certainly this is kind of a motivation that we do need to take the issue of injection-induced seismicity at CO2 projects seriously, because we are injecting very large volumes, very high rates into the subsurface, rates higher than we know have triggered seismicity. Moving on now to that issue of spatial distribution. For these various projects, the injection well is essentially 0 here, and these are histograms showing how far away from the injection well the seismicity occurs. So in pretty much all cases, you get some seismicity that's pretty much at the injection well, and most of the seismicity within 5 kilometres. So there's a kind of estimate of your, how far away do I need to consider in terms of faults that can be reactivated. 5 kilometres for most of the earthquakes, but we see some tails out. Some of these tail all the way almost out to 20 kilometres. So at a maximum limit, maybe we need to be looking further out. Are there faults within 20 kilometres of my injection site? Because we think we've seen fault reactivation as far as 20 kilometres away from injection wells and some of these wastewater disposal projects. Now considering depth. Again, I've normalised all these instances so that the bottom of the injection well is at 0 depth here, and then the histograms. And what you can see from this is that in most cases you get some seismicity at the depth of the reservoir. So we're starting to trigger a fault that's in the reservoir, but then the vast bulk of the seismicity is well below the reservoir, often 2 kilometres, 3-4 kilometres below the reservoir, and often in the kind of metamorphic basement that's below the sediment. It's not even in the sediment column, it's in the basement.
Could you clarify, is that frequency or magnitude?
This is just the number of events. This is the number of events as a histogram against depth. So there's a good news and bad story to this slide, I think. The good news is we don't tend to see much seismicity going above the reservoirs. So when we talked about the integrity of the cap rock and the potential for CO2 leakage, beyond the fact that active faults don't necessarily provide a leakage pathway anyway, especially in shale rocks, just because you've got a fault doesn't mean it's going to leak. But even so, we don't tend to see faults that are being reactivated above these reservoirs, which has got to be good news in terms of storage integrity. But on the flip side, you have the issue of site characterization. I'd be pretty disappointed if any of you guys had a potential storage site and you weren't able to identify faults in the reservoir on your 3D seismic surveys, which of course you're all going to do before you start injecting. But the resolution of seismic surveys decreases with depth. So as you go down, it gets harder and harder to see things. So we can see that faults that may be kilometres below your injection site could be reactivated and give you seismicity. And these will be substantially harder to pick up in your reflection surveys. So we might do a reflection survey and say, well, we can't see any faults, we think we're happy. There could still be a fault a long way below the reservoir, that there's a potential for it to be reactivated. So I think just because you haven't got any faults doesn't mean you shouldn't be monitoring for things like induced seismicity. I think is the conclusion we take from Just going to move on to a couple of case studies now. These are projects that I've worked on during my PhD in research at University of Bristol. So three of the kind of major, really large-scale CO2 injection projects: Sleipner in the Norwegian section of the North Sea, Weyburn, Central Canada, which is an EOR project, and Insala, North Africa, which has been mentioned a couple of times in the last couple of talks. I don't actually have any slides of Sleipner because really there isn't anything to show for Sleipner. Sleipner is a very large sandstone aquifer with incredibly good flow properties. Its permeability is Darcy scale, its porosity is something like 35% porosity, and it extends under a huge amount of the North Sea. It's a really large aquifer. And so on a volumetric basis, the CO2 that's been injected into it is a fraction of a percent of the whole pore volume of this single formation unit. So there's been, and with the really good flow properties, there's been almost no pore pressure change or any kind of geomechanical effects whatsoever. So Sleipner is an absolutely ideal place to put your CO2. It's soaking this stuff up like a sponge with very little geomechanics at all. So if we can find lots and lots and lots of Sleipners, then that is really good news. But as we said, we're going to need hundreds and even thousands of CO2 injection projects around the world to make CCS effective from a climate perspective. So I think the question is, can we find enough places that are like Sleipner? Because Sleipner is pretty much perfect, but can we find enough places like that? Moving on now to consider Weyburn, Central Canada. This is an EOR project. It's a really mature field, first developed in the 1950s, produced under water floods. This is just the oil production rate. In the 90s, they kind of tried to increment the oil production by drilling horizontal wells. And then from 2000, they've been injecting CO2 for EOR. So so initially when they found the field, they estimated 1.4 billion barrels of place, of which before CO2 injection they'd recovered 370 million barrels. They're injecting about 3 million tons of CO2 a year, hoping to recover another 130 million barrels of oil. So whilst there is a research project running to study the effects of CO2 injection, for the operators this is a very commercially viable and valuable project for them to get a lot of extra oil out of the ground. So that's why they're doing this, and that speaks to the use of, this has been discussed in the morning, the use of EOR to kind of help push CO2 storage further down the line. Just to give you an idea of what the field looks like using some of the seismicity results. So these are maps showing changes in amplitude and travel time shift through the storage reservoir layer. And the way the field is set up, you have these horizontal producers and then horizontal injectors kind of next to each other. So you kind of go producer, injector, producer, injector, producer, injector, kind of horizontal wells. And where the CO2 is being injected, you can see the changes in reflection amplitude and the time shift caused by the changes in the physical properties due to the CO2. And on the right here is a flow model. This is where they predicted the CO2 should go. So you can see, just looking by eye, there's a pretty good match between where the CO2 is going and where the CO2 is going from the seismic and where we model that the CO2 should go. So that's all good news in terms of reservoir behaviour. The pressure history of the field. So going back to the 1950s, initially production was unsupported. So we started at hydrostatic 15 megapascals, and as we sucked all the oil out, the pressure dropped substantially, down to almost 5 megapascals. Then they started re-injecting water to support the pressure in the reservoir, which kind of kept the pressure around about this hydrostatic value of 15 MPa. And then since CO2 injection, the average pressure has increased slightly, so we're kind of moving up more towards 20 MPa with the additional pressure of injecting the CO2. But that's not a uniform pressure across the field. You have substantial pressure variations across the field. So this is kind of a map view just of a segment of the field, and you can see the scale here from sort of 16 up to sort of 21, 22 MPa variation. In some parts of the field, production is dominating and the pressure is lower, and in some parts of the field, pressure is elevated where kind of injection is dominating. So you've got a slightly more complicated effect. It's not just a single pressure increase or pressure decrease. We've had 50 years of pressure going up and down, and we have substantial pressure variations and gradients in pressure across the field. So it's a little bit more complicated, which is kind of the theme for Weyburn, which I'm going to kind of elaborate on in the next few slides. Microseismic monitoring was installed in a small part of the field. So the black horizontal lines here. These are the production wells, and there was a vertical CO2 injection well in between these 4 production wells. And next to the injection well, they installed 8 geophones on a downhole borehole to listen out for any microseismicity. So this was only a very small part of the field. Weyburn's a big field, so this is only an experiment in a small part of the field. This wasn't meant to be kind of a comprehensive study of the whole field. It was just an experiment in a small part of the field. So we monitored from September 2003, when injection started in that well, to January 2010, when injection finished in that well. And we picked up something like 100 events, magnitude -3 to magnitude -1. So these are very, very small events. They're micro-earthquakes, as they're referred to. So magnitude is a logarithmic scale, so these are millions of times smaller than what we usually call an earthquake. Referring again to Dr. Durr's advice, he said use an analogy as well. Well, I've got a good analogy for this one as well, is that when I used to be a kid, I used to get hungry in the night and I used to try and creep down to the kitchen to get some chocolate to eat. But we had floorboards in our house that used to creak. When you step on them, they go, "Arr!" And that would be how my parents would know that I was sneaking downstairs to try and steal a biscuit or something. This I like to refer to as a lot like that. It's not really an earthquake, it's more that the reservoir is just creaking and popping as the CO2 is moving through it. And we're using those creaks and pops in the same way that my mother used them to spot that I was trying to steal a biscuit, to try and see where the CO2 is moving through the formation. So these are really, really small events, but they tell us something useful because they tell us how the reservoir is responding to the stress changes that we've imparted by injecting the CO2. And this is just a map view and cross-section. So the interesting fact is that in map view, actually most of the events were around the production wells. So this is the injection well, these are the production wells, and actually most of the seismicity was around the production wells, not around the injection wells, as you'd expect, which is somewhat of a counterintuitive observation. We also viewed in depth here. The important observation here is that you don't want to see seismicity creeping up towards the surface. The cap rock, is several hundred meters thick, so it extends up here. What you don't want to see is microseismicity going through the cap rock, charting a fracture moving up through your cap rock. So all the seismicity stayed pretty much around and just above the reservoir, yes, but it didn't move substantially through the cap rock. So we're happy in terms of CO2 containment. And then just after they finished injecting, in September 2010, approximately another 100 events occurred all around the injection well at the reservoir depth, which is really surprising because the pressure is dropping at this point, and then suddenly we get seismicity. In the interest of time, because I think I haven't got a huge amount left and I want to talk about InSala as well, I won't go into detail about this. To be honest, it takes me about half an hour just to explain these observations. It's quite complicated in terms of stress redistribution, stress arching, and stress transfer through the rocks. But actually we found out that because of the long production history in this reservoir, it's actually more likely to get seismicity where pressure is going down instead of where pressure is going up because of the compaction of the reservoir in this particular case. So during injection, pressure is going down around the production wells, and that's where we've got seismicity. And then once pressure drops around the injection well after shutting, we get seismicity there as well. So the kind of take-home message I get from Weyburn, firstly, as my analogy said, listening in with really detailed monitoring to these pops and creeps can tell you a lot about how the reservoir is responding to stress, and you can learn a lot about what's going on, which is really important. And secondly, EOR great for the commercialization of CCS because you get to make a profit while storing CO2. But if you're going into some of these mature oil fields with a long history of doing stuff to them, you can get some surprising effects. It doesn't always behave exactly as you expect because you have kind of complex, inelastic stress effects. So some people sort of imagine that if you take the pressure down and you return the pressure back to where it was, everything will be exactly the same. And it's not. There's hysteresis. It's inelastic. You don't necessarily end up where you started just because you moved the pressure back to where you started. The stress may be very different. And that's kind of what we saw at Weyburn. Moving on to InSala now. This is in the middle of the Algerian Sahara Desert. So it's a gas production field. The gas has quite a lot of CO2 in it. So the gas is stripped and re-injected. It's not re-injected into the gas-bearing part of the reservoir. It's re-injected into the water-bearing limbs of the anticline, slightly away from where the gas is. And they've been injecting since about 2004, in total just under 1 million tonnes of CO2 a year. Here's just a map of the reservoir. So this is the gas-bearing parts on the centre of the anticline, and 3 CO2 injection wells around the sides of the reservoir in the water-bearing part of the reservoir. The flow properties in the reservoir aren't great, to be honest. Porosity average only about 0.13 or 13%. And permeability, really, we're talking about the millidarcy range here, so not particularly great flow properties when you compare that to Sleipner, for example, which is 1,000 times more permeable. And as a result of that, you've had substantial increases in pressure around the injection wells and very little kind of pressure communication between the injectors and the producers. If you're taking gas out in one place, you're putting gas in another, but that's not leading to an equilibrization of pressure. You've got high pressure in one part, low pressure in another. So these are the pressures going up around the 3 CO2 injection wells from hydrostatic at 18 MPa, sort of 6 or 7 MPa increase, while at the top of the reservoir in gas-bearing parts where they're producing gas, drop of sort of 4 to 6 MPa on the sides. So again, substantial pressure changes because of the injection production, which is mainly a factor of this low permeability. As a result of those pressure changes in the reservoir, we've seen substantial amounts of surface deformation, which I think some of you are familiar, given by some of the comments you've had in some of the other talks. But at the 3 injection wells, we've had uplift of several centimetres, and above the gas-bearing part of the reservoir, subsidence. Now, of particular significance was the uplift around this well, because the uplift around these 2 other wells is just fairly kind of oval-shaped, ellipsoid, not a lot going on. But you'll notice this uplift has this kind of lineation going through the middle of it. And if you know your surface deformation and your INSAR, that can be an indication of a fracture zone at depth, which obviously is of concern because you don't want to be having fracture zones where you're injecting CO2 for secure storage. That led in 2009 to the installation of some microseismic monitoring. Now, sadly, this is 5 years after they started injecting, so it would be really nice to have this in from the start rather than 5 years too late. I also don't want to be too harsh on the whole installation, but the operators were trying to do it very cheaply, and as a result, it didn't really work that well, and actually only 1 of the 6 geophones they put in actually functioned properly. So that's a bit of a disappointment, because to locate earthquakes you need multiple stations for good triangulation. So with only 1 station you can't do triangulation very well at all, or you can't do it at all in fact. So we can't really properly locate the seismic events. We can get an idea of where they're coming from, but we can't properly locate the micro-earthquakes. But what did we see? Well, they put them in 2009 and started injecting again, and the injection rates and pressures are shown in red and blue, and the number of events are shown in black. And you can see that when they really ramped up the injection rates through this well KB502, we were recording something like over 2,000 events a month. So we're looking at sort of hundreds of events a day being recorded. Again, these are microseismic events, so low magnitude, but higher magnitude than Weyburn. So this is a plot of magnitude measured using the, again, we can't really get proper magnitudes without a good location. But these are estimates of magnitude using the S wave and using the P wave. But the majority of events have a magnitude around about 0, so it is larger than what we saw at Weyburn, which was -1 to -3. And the largest event had a magnitude somewhere close to 2. Now, it depends where you are in the world as to what you call that. In the UK, even a magnitude 2 event is considered fairly significant, definitely considered an earthquake. Perhaps in Taiwan, I think magnitude 2 is slightly less important given the number of larger events you guys have. But it's still verging on inducing a proper earthquake, not just the kind of the popping and the creaking of the reservoir. Now, as I said, we can't properly locate where the events are accurately, but we can look at kind of the direction of the geophones of where they came from. So the geophone was directly above the injection well, and that's kind of a stereo plot of where these events are coming from, kind of find the geophone looking down into the ground. Where are these things coming from? And then they're coloured by the amount of time it took these events to arrive. So that's obviously a function of depth. So the deeper you are, the redder this colour will be. So blue corresponds to roundabout, approximately, this is not accurate at all, but approximately, blue is the depth of the reservoir. And then red is deeper than that, or further away than that. So the two things we know from this, it seems that we have a fracture zone that's striking sort of northwest, southeast, and that there's no change in the travel times through time. This zone is staying where it is. Again, we talked to Weyburn, the concern is if you start seeing fractures moving up through your overburn, and I don't think that's what we see here. They stay in the same place. So there's an active fracture zone, but it's not an active fracture zone that's growing upwards, which would be the real concern. And we can kind of put all that together. So the inversion from the surface deformation suggested an open fracture zone centered on the reservoir, maybe going 100 or 200 meters up into the overburden. On the reflection seismic, they saw this kind of anomaly in the same place, striking northwest, southeast as well. Again, extending from the reservoir maybe a couple of hundred meters into the overburden. And that all fits in with what we see from the microseismic as well. So all our different geophysical observations are kind of telling us the same thing. We've got a fracture zone active in the reservoir, maybe going a little bit into the overburden cap rock, but the cap rock at Insala is a kilometre thick. So there's still a lot of cap rock between where this is going on and the nearest kind of aquifer that we might want to protect from CO2 leaking into it. So, you know, it's an interesting observation here. I don't think there's risk that CO2 is going to leak through a kilometre of cap rock. And so my sort of take-home message is, most important thing is, if you've got lower permeabilities, you're more likely to get these pressure increases and more likely to induce seismicity. Put monitoring in from the start. 5 years after you started injecting, suddenly you decide you might induce seismicity might be an issue. It's too late by then. You know, it's a real disappointment that this stuff wasn't in by the start. We'd have learned a lot more had that been in from the start rather than waiting for 5 years and then putting it in. But I guess the final take-home message is that the more cap rock you have, the more secure your storage is. So if you're worried about fracturing cap rock, well, if you've got a kilometre of it, that's a long way for a fracture to go. If you've only got 50 metres or 100 metres, maybe a fracture you can get through that. But if you've got a kilometre, that's good news in terms of storage integrity, which is really what is good about Insala. If the Insala cap rock had only been 100 metres, 200 metres thick, I think the concerns would have been substantially greater in that regard. So, nearly dinner time, just about to time. So, just some conclusions now. So first of all, looking back to those examples from waste fluid injection in the US oil industry, I think it's really important that CCS learns a lot from these. There aren't many CO2 storage projects around in the world yet, which means it's sometimes hard to have data. But there's a lot of other operations that inject fluid into the subsurface. And I think we as a community need to be going out aggressively, finding people that have injected fluid into the ground for other reasons and talking to them, finding out what worked, what didn't work, and what we can learn about what happened from that. And so, for instance, in this case, my kind of conclusions are, radius of influence for your injection well, we see induced seismicity up to about 20 kilometres. So that's kind of got to be your kind of requirement for looking for faults, building your models, etc., etc. But the majority of earthquakes occur below the injection well. So this whole issue was really blown open by Mark Zobak, a professor at Stanford, who said the earthquakes are going to cause CO2 to leak. I'm less sure of that conclusion, A, because faults don't necessarily leak just because they're active, and also the majority of deformation we see actually occurs below the reservoir, which isn't a concern for leakage. But some other things. Firstly, again, going back to the monitoring, underground water injection people, they like to do it cheap, they don't want to have to monitor, which means often we're coming into this after an event's been induced, and then they go, oh, we better put some seismometers out because it caused an earthquake, which is too late. Awesome, stable door bolted and all the rest of it. So, put these things early, and that means if something goes wrong, you're in a good position to detect it and work out what's going on. Don't wait until you've caused an earthquake and then put the seismometers out. As I say, so get the local networks deployed early rather than waiting until it's happened. To learn from existing CO2 storage operations, Sleipner's a good example, really good flow properties, really large aquifer. So that's the kind of thing we should be targeting to minimise pressure changes and induce seismicity. but we need 10 billion barrels of storage per year approximately if we're going to make a difference for the climate. Can we really find enough slightness? From Weyburn, we learned that if you're using mature reservoirs, it's great for EOR, from a commercial perspective, but things can get complicated. You have this kind of hysteresis and stuff, so it may not be as simple as you might think. And then finally, what we learned from Insala is that if you've got a not great reservoir and you think it's going to deform a fair bit, then at least have a really thick cap rock, because even if you have some deformation, the cap rock thickness will save you. And then finally, and I think it's something that's been touched on by a lot of the previous speakers, but this kind of systematic geomechanical appraisal prior to injection is essential. So are there any faults or fractures within 20 kilometres of your injection well? And then numerical modelling. That's one thing I didn't see actually in the last few talks. I saw models of the pore pressure, and well, I didn't see pore pressure actually. I saw models of saturation. I didn't see anyone modelling how the pore pressure is going to change. And then following on from that, how is that pore pressure change going to affect the stress on that fault? Because it's the stress on the fault, how much you're squeezing it and how much you're sliding it, that's going to control whether that fault reactivates or not. So models that work out, you can do this with fine element techniques. My injection well's here, my fault's here, how much is my stress going to change on that fault? And is that going to be a potential risk for induced seismicity? As I think I've got the point across by now, but get your monitoring in early and get lots of it in, because then you can see what's happening. And maybe these pops and creaks, these microseismic events, might be able to warn you that a fault's at risk of reactivation, or that your cap rock's at risk of fracture. These things can really tell you a lot. And finally, I've seen a lot of geomechanical models, and there's a lot of numbers in geomechanical models that you can change and get a different answer. So you build a geomechanical model to start with, but once injection starts, make sure your geomechanical model agrees with your observations from your field. And if it doesn't agree, it's not the field that's wrong, it's your model that's wrong. If your model's not agreeing with observations, you've got to change your model and make it fit your observations. And then you have confidence that your model's telling you what it's supposed to. And if your model's telling you your fault's not going to reactivate, then you can start to be happy. So that's briefly acknowledge my co-authors, co-workers at Bristol, Professor Mike Kendall and Dr. Anna Stork. This work is variously sponsored by NERC, which is the UK Natural Environment Research Council. BP have funded a fair bit of our work, and the Petroleum Technology Research Centre in Canada, which funded a lot of our work on Weyburn. And then finally, for permission to show data, the Insala JRP, which is BP, Statoil and Sonatrach, and the operators of Weyburn, so Cenovus and the PTRC. And any more information about our research group and our spin-off consultancy group, there's websites there for you to see. So thank you very much.
Thank you so much.